Hello everyone, welcome to this short video, which is a sort of a presentation where I will try to give you an overview of our recent projects which we are doing in the area of AI and machine learning based engineering solutions. Most of these works are applied stage, which is high TRL, technology readiness level, and they can be used in the industry. So hopefully you will like them. If you are really interested in any of these projects, and if you want more details on that, then please get in touch and definitely I will provide more details on it. Also, if you want to learn about how these things are done, then please also get in touch and I can make short videos or tutorials on how you can do similar sort of analysis and produce simple similar solutions which can be used for different applications. Okay, so when you're using machine learning or any deep learning or any other algorithm as a black box, we are not the developers of machine learning algorithms, but in this case, we are using them as a tool. So it's the same as when we do FE analysis. So most of the time we are using a commercial finite element software to perform analysis, but we still need to understand what is happening in the background. So general methodology is you start with the data collection for a specific problem. Then if you have the data or if you can find or identify which data is missing, then you can use mechanistic models like FEA analysis or probabilistic analysis or do some experiments to generate more data so that you have enough data to train your models and test your models. So once you have that enough data available, then you go and select appropriate machine learning based algorithm and then train and test the model. And once you have done that, then you do validations and verification by giving some unseen data or unpredictable data and see how the predictions really look like for that specific problem. And finally, if everything is working fine and you are happy with the results and your results are very close to the reality during the validation and verification section, then you can use it for your real life application. Again, this is not a very straightforward process as shown in here. It's a complex iterative process. So when you are doing, for example, training and testing, so you might have to go back and collect more data. You might have to go back and do additional experiments or do extra runs for FE analysis to generate more data so that you can train and test better. Also, when you are using in the real life, then since you use the data which is like in the lab environment, if you get more data from the real life application, then you can again come back and you can keep on inserting that data which you already have in your machine learning algorithm to further enhance their training and testing so that you can have more better prediction and your confidence level goes high in the whole thing. Again, using this is a generic methodology which you can use for any application when you're using a machine learning or AI based algorithm. But the main question you have to answer is what data is needed, how much data is needed, and where to get the data. And I think if you look at that previous diagram, I explained to you how to answer those questions in this simple block diagram. People think that if they know machine learning, then they can do anything in this world. It's not like this. The main questions are on the screen right now, and or whoever is data rich for a specific application, they will lead that area of research. So again, these are the key questions we always try to answer for a specific application. So in today's presentation, I'm gonna very briefly, no details on how it was done, but just the outcomes and what was done. I have selected these 5 projects. So I will start with predicting wind turbine blade composite damage, how you can train the model and what could be the outcomes of that. How can you predict the biologically influenced corrosion, MIC, if you're familiar with that. And also you don't need to have a specialized knowledge in that. You can just, if you have the data, you can use machine learning, train it, test it, and then use it for your real life application. Also, if you're designing a wind farm, then the layout of the wind farm, that how far should be the wind turbines from each other, how they are arranged in the wind farm, it's kind of an optimization problem. So we have tried that also through machine learning and similar approaches. Also, if you have a wind turbine which is operating in a wind farm, then you have a lot of erosion due to rain droplets, sand blasting, whatever. So we also did some erosion modeling through machine learning. And finally, if you have a wind turbine which is operating and you have wind turbine blades which are always rotating, and if there are defects or that damage which occurs in your blades, then how can you detect them early so that you don't to avoid the catastrophic failure, and you can do some remedial action before that. So again, we use machine learning for that. Okay, so I will quickly go through it. Let's start with the first one. In this case, what we did was, again, I will always give the credit to who has done it. So he was one of my MSc students in renewable energy engineering, Zongchun Huang, and he developed a feed-forward neural network (FNN), and he was able to predict the composite blade damage as well as the stresses in the blade using a feed-forward neural network, or FNN. So again, you can see, if you're interested in this application, then you can always get back to us. Again, the cycle is very much the same as I showed you before: collecting the data, defining the data, data analytics, and then testing, training, and then go back and see how you can improve that, and so on, and finding those answer to those questions about the data. Okay, the next one is the microbially induced corrosion. In this case, if your structure is basically in a subsea environment, or in any environment where you have microorganisms such as sulfate reducing bacteria, iron oxidizing bacteria, or sulfur oxidizing bacteria, etc. So if you have different bacteria, they can cause degradation and corrosion in your material. So in this case, we did that, and again, we use support vector machine algorithm, and you can see how the pitting depth is predicted as compared to the actual values, and you can see they match really well. So we were able to train, test, and predict the pitting depth for different cases, scenarios. And again, these results are not from the seen data, but these are predictions from unseen data. So this is one thing we did. Then wind farm layout, as I explained to you, you have a lot of complex interaction between the wakes of different wind turbines depending on the wind direction. So you have almost 10 to 15% electricity production loss due to wake, right? So, and they interact with different wind turbine wakes, interact with each other. So it's a complex process. So we basically worked on that. And in this case, normally what they do when they are arranging the wind turbines, they use heuristic algorithms, which are very slow and they take a long time. So we have developed a novel scaled layout kernel, SLK, and we interfaced it with machine learning to solve this wind farm layout optimization problem, which we call WFLOP. So by doing that, you can see this is the heuristic optimizer, which took a very long time to solve. These are the wind direction, and these crosses are the wind turbine arrangements in the wind farm. And you can see how it looks like for the SLK. And we can see that our SLKs, it had better fitness by SLK than the heuristic optimizer. So results are very good, and obviously computational time is very small as compared to the traditional heuristic optimizer. Again, this work was done by one of my MSc renewable energy student, Noah Renessen, and he did some remarkable job in this as well. So at the end of the day, we basically use machine learning to predict the optimal farm fitness. And we found out that error slightly higher than the heuristic optimizer and perform slightly worse than the heuristic optimizer if we are looking for the farm fitness. We also tested machine learning for predicting the optimal number of wind turbine, and in this case, the error was lower than the heuristic optimizer, and it outperforms the heuristic optimizer. So this was better in this case. Then the novel SLK technique, which we developed in this work, outperforms the several heuristic optimizer algorithms for all cases examined, and optimization time reduced by 99.9%. So you see, we save a lot of time here while using this kind of SLK technique as compared to the heuristic optimizer. So this was again very good, excellent work done by Noah, and I really appreciate that. Then another project we did was erosion modeling of wind turbine blades. So wind turbine erosion is a big problem, as you see on the screen, and again, you have a lot of energy loss, and when energy production loss is 25% based on this, because your aerodynamic performance goes down because of that. So again, what we are trying to do here, we are trying to combine the design and integrity problem and with the digitalization. And this project basically is a frontier of those two cases. The work was done by Teolua, and he was again an MSc renewable energy student at University of Aberdeen, and again he did a very good job. So in this case, what he did, again, the same data analysis, pre-processing, collection of data, selecting different types of machine learning algorithms. So in this case, we tried support vector machine, artificial neural networks, and also random forest models. And at the end, select the appropriate one, and then use the final validation, giving it unseen data and use it for real life scenarios. So again, you can see the predictions from the random forest algorithm, which was found to be the best for this application. And these are the actual and predicted values. So again, we had an optimal accuracy of 99.42% to predict the erosion damage rate. Last but not the least is the early stage damage detection in wind turbine blades through machine learning. This was done by Timothy Him. And again, he was an MSc renewable energy student. So again, in this case, what we did was, if let's say if your wind turbine is operating in a certain environment, and if there is a damage in the wind turbine blade, and if you have some sensors which can measure any anomaly or which can measure the strains, for example, in this case, then machine learning can predict the undamaged strains, and the damaged strains which are measured from the damaged blade through sensors or strain gauges are compared with each other after training and testing, and we can see that there is the system can detect anomaly in different regions if there are any. So we basically use it. So when you look at this figure, the damaged regions are measured data sets. So these are the measured data set which is coming from either sensors or strain gauges, while undamaged region here in the graph means the machine learning predictions for the same amount of displacement in the or deflection in the blade, what sort of strains will be there. This is machine learning algorithm is trained for undamaged blade because we know the initial geometry, and without damage we just train the model based on that. So it can basically find anomaly anywhere in the blade, and it can trigger the site engineer that, okay, something is wrong, you need to go and check those areas or those regions of the blade. So again, this was another excellent project, and some good results we obtained from this as well. So you can see these are some of the few of the examples I gave you today. So if you are interested in any of those projects or similar projects, or you want to use machine learning for other applications or other ideas, then you can always get in touch with me, and I'm really happy to help you and discuss ideas with you guys. So for any further collaborations. So thank you very much for watching this, and I hope you enjoyed what we are doing, AI and machine learning in engineering applications. So see you with some other interesting videos soon. Please comment below if you want to have any tutorial related to one of these problems, and I will try to make one in a simplified manner. So thank you, and bye for now.